Alright, so last time you guys were looking at this lab where you had to collect data for angular acceleration and angular acceleration and mass, which we're actually going to convert into a force. Now, this is the issue. We actually didn't measure torque directly. Okay, here's the numbers that my class got. I more or less rounded, but they used 15, 20, 25, 30, 35 grams, and so convert that to kilograms. These are the angular accelerations they measured, give or take a little. Okay, they're negative because this thing was falling down, although we're going to kind of ignore that in a minute. It's a direction indicator, not a value indicator. Remember that. Okay, so this is where we're at. I think you guys had similar data to this. Now, did the disks resist the motion of the hanging mass, and how can you tell? Well, if you look, two disks had almost half the angular acceleration of one, so yes, they did. If they didn't resist the motion, then the mass wouldn't have mattered. The number of disks wouldn't have mattered. Okay, now this part is where it starts to get a little bit fuzzy, because since we're actually trying to find a relationship between torque and angular acceleration, but we didn't measure torque. We measured angular acceleration, and we know the mass of the hanging object. We know the mass of the thing that's applying the torque. Okay, and so I kind of have that picture drawn out here. Well, let's take a look at where this equation comes from. I can't remember if we've done this before or not. Okay, when you have a cart being pulled along the tabletop, like this shows here, there are several forces at play, but one of them is important. Okay, and it's not mg, it's ft. So let's take a look at that. Okay, this cart has the net force Ft acting on it. Okay, and that's the tension in the string. It's caused by this hanging mass, and mg is pulling down. But that's not the only force acting on that. Ft is also acting on it. Now, if we take this way to be the positive direction, then what we can say is we can say Ft is equal to what? Okay, well, if we look at this thing, just this part of it, we can say the net force over there is equal to mg minus ft, and according to Newton's second law, that's ma. Okay, and so then I have ft equals mg minus ma. Okay, and so this allows us to say the size of the force acting on the cart in terms of the falling mass. Now that's handy because we know everything about the falling mass on that torque problem. So if we can go back down to that, we can solve for the torque applied based on the mass and acceleration of the falling mass. Okay, and so we have sort of the same issue. From the top down, you've got a big disk that's attached to a smaller pulley, and that pulley's got a string wound around it, and then this whole thing was being pulled Ft. Now, there's a torque right here, right? Because this pulley is being spun in a circle, and circular motion is caused by a torque, and this torque is caused by this force Ft. So I can say the net torque acting on that pulley is equal to force Ft times lever arm R. And since this is a 90-degree angle, I don't have to worry about the sign. The sine of 90 is 1. Okay, so now what I need to do is I need to say, okay, well, what's Ft? I didn't measure Ft, I measured acceleration. Okay, and I didn't actually measure acceleration, I measured angular acceleration. So let's think about that. Okay, we have this equation from up above, Ft equals mg minus ma, where this is the falling mass. So if we use that equation here, we can say, okay, well, that means the net torque acting on that pulley is given by mg minus ma times r. But I don't know a, okay, right? We were measuring the the angular acceleration of that thing. So what I want to do is I want to replace a with angular acceleration, but we can do that because we know a equals alpha r. So I'm going to go ahead and say, okay, that means net torque, which is force times lever arm, is mg minus ma, which is alpha times r. That whole thing is times r. So I get mgr minus m alpha r squared is equal to the net torque acting on that pulley, causing everything to accelerate. Okay, now that tells me how to find net torque, but remember I'm still trying to actually find a relationship between net torque and angular acceleration, right? Because this equation tells me the relationship between force and torque. I want to know the relationship between torque and angular acceleration, because after all, torques cause rotational motion. They cause angular acceleration. Now, this part of this lab assumes you have some software that you probably don't have. Okay, now that's okay. You just have to do a few calculations. Okay, so here's what I need you guys to do. In your calculator can do most of this work for you, or you can do it by hand. But if you have your calculators, here, let me pull up my calculator. We're going to use the calculator to actually calculate a whole bunch of values for us. Okay, so we have the equation net torque is equal to mgr minus alpha, angular acceleration, r squared. So we want to use that equation and all our data in order to get torque, and our calculators will do that for us. So on your TI calculator, if you do stat, edit, and I've got a whole bunch of information in my lists, okay? And I want to put in the masses. Oh, look, I already did. If you have a whole bunch of information in your list, all you do is you arrow up to the top and push clear, and it'll clear all that data, okay? Now you can enter your numbers, right? So I have 0.015, okay, and 0.02, and 0.025, 0.03, 0.035. Okay, so I have my masses, and I don't want the mass in grams, I want it in kilograms, because force is newtons, which is kilogram meters per second squared. Okay. Now, what I want is I want this whole equation right here, mgr minus m alpha r squared. Oh, well, I need another term then. Okay, so over in L2, I'm actually going to put my angular accelerations. Okay, so again, I have a whole bunch of stuff in there. I'm just going to clear it. So arrow up to L2, push clear, and enter. And now I can put in my angular acceleration values: 25, 32, 37, 45, 64. Okay, and one more time in L3, I'm going to put my second angular acceleration values. So again, clear in whatever information is in there and enter. And so now my second angular, whatever, you guys know what I'm doing, 15, 20, 24, 28, 33. Okay, your values might not be exactly these values. I took the class and averaged it real quick. It's okay, yours should be close, but it won't be that big of a deal if they're a little bit different. Okay, now here's what I just did, and I'm going to make a note of this to remind myself of it. I have this in L1, I have the angular acceleration in L2, and I have angular acceleration 2 in L3. Okay, so I noted that on my lab sheet so that I can keep track of what's going on there. And so now I'm going to have my calculator do some work for me. It's going to do this equation, right? I either have to do this 6 times or 8 times or whatever, or I can have my calculator do all the work. I'm all for having my calculator do the work, but you have to pay attention. Okay? So up in L4, I have a whole bunch of numbers. I'm going to clear that out of there. Okay? Clear that. And now I'm going to arrow back up to L4. Okay? And I'm going to put an equation in there. I'm going to put this equation, this mgr equation in there. Okay? So m, which I have in L1, so I need to put in L1. So I do second list L1. Okay? Times g. Well, g is just 9.8, so times 9.8. Times r. The radius is 0.025 meters, I believe. It's whatever you guys found when you did your angular acceleration before. Okay, so that's the first part of it. Now I need to subtract off that second part, m alpha r squared. Okay, so I'm going to put this in parentheses so it doesn't get confused. M is again given to me in L1, stat, edit, not stat, sorry, second list, which is above the stat button. L1 is the mass, so I want L1. Alpha. Alpha is, we're going to have to do this twice, right? Once for L2 and once for L3. So I'm going to take this times second list L2, okay, and then times finally R squared. So 0.025 squared. Close your parenthesis and enter. And it generates all the values for you. Now, I want you to pay attention. It actually shows one value here, but if you arrow down to it, it puts another value in right here. Okay, so L4 has got our torques for the first disk, for a single disk, and we can do the same process in L5 to get our torques for the other ones. Okay, once you have that information, you're ready to actually plot some points. Okay, and so this is actually sort of like Newton's second law. When you have F equals ma, okay, we want to find the relationship between torque and angular acceleration. And so what we want to do is we want to create a graph that has torque on the y-axis and angular acceleration on the x-axis. If it's a line, then we can conclude something about the relationship between torque and angular acceleration. So let me open graphical analysis, okay, because that's where you're actually going to do this calculation. Okay, so in graphical analysis, there's a way to manually enter data. And so up here on the right, I'm going to push plus manual entry, and then I need columns in X and I need columns in Y. X is going to be angular acceleration. Okay, so if you push and hold X, it lets you give you a column title, and so angular acceleration, and this will be for part 1. So I'm actually going to write angular acceleration 1, and the units are radians per second per second. Okay, it doesn't really matter if you get that in exactly right. Okay, and now you can actually put in that data that you have from your lab sheet, right? So my angular accelerations were, let me pull this information open, I had 25. And you guys want the positive values for angular acceleration, okay? We already subtracted it in the equation, so we want the positive values. 25, 32, whoops, I don't want that in Y, I want that in X. 32, 3 was 37, 45, and 64. Okay. 45, 64. Now, over in the Y values, we want torque. Okay, and again, this is torque for the first one. So I'm going to have torque, column units, Newton meters, and so torque 1. All right. And then these are the values that your calculator gave you. So if you open your calculator back up, okay, then you can copy in the values from L4 for torque. And so I'm going to have 0.00344. 0.00344, and just follow along down the line. 0.0045, 0.00555, 0.00651, and 0.00710. I have to double check. 0.0071718. Okay, 0.00718. All right. So now I've got in my angular acceleration and my torque, and I want to see the graph of that. So I'm going to say, okay, show me a graph, one graph, and across the bottom it's got my x values, which are angular acceleration, and up the side it's got my torque, which is torque. Okay, and so now I've got this pretty little line, okay, and I can do a linear fit on it. I can highlight all that data. I can say, okay, what is that? Let's see, linear, add, okay, not bad, not perfect, but not bad, okay, and okay, now that doesn't mean anything in and of itself quite yet. We also want to do that same thing for your second torques, okay, so back on your data table, actually, let's see, I think that was under the graph button, we go table. and I'm going to go ahead and I'm going to add manual column 3 and manual column 4. And in these ones, again, this is going to be your angular acceleration for 1 and 2. So I'm going to have AA2, and I'm going to have T2. Okay, again, radians per second squared, and torque, T2 Newton meters. I don't know why it's trying to get me to do NMR. Okay. And now you're going to have to do this in your calculator again, right? We need a second list, and I think I actually already have that in L5. I think I already put in that equation, and it's just like the one from before, only you use your L2 value or your L3 values instead of your L1 values. Okay, but I'll clear that out and show you one more time how we do that, right? So in L4, or I guess L5, I want this to be equal to MGR, so M is L1, second edit, second list, L1 times 9.8 times 0.025 minus, parenthesis, M, which is still L1, second edit, L1, times G 9.8, whoop, not G, M alpha times alpha, which is this time going to be in L3 because it's our other angular acceleration. So second list L3 times the radius squared times 0.025 squared, close my parenthesis, and enter, and it generates all those values. And so now I can put these values into my second row on my graphical analysis app. So let's do that. Okay, second column, angular acceleration 2. My second, my values for these were about half the ones I had before. I have 0.15, and then my torque 2 are my values off my calculator, and so 0.00353, 0.00465, 0.00575, 0.00575. Hey, that one didn't get my 0.00575, 0.00683, 0.00683, and 0.00785, 0.00785. Okay, done. And now I'm going to go back to my graphs. Okay, so actually I think the best thing that we're going to have is once we get our data entered is if you do 2 graphs instead of 1 graph, because then you can separate out your values. So up there I just choose 2 graphs, and then over here on the left side I have the first torque, and on the bottom I have the first angular acceleration. Same with this graph, I have the second torque against the second angular acceleration. And then I highlighted those and I got linear fits for both. Okay, now the thing that we're really interested in on that part is the slope of the lines. And if you look at that, let's see, I'm going to go ahead and I'm going to open this information, the graphs, into Notability real quick so I can draw on it and show you what's going on. Okay, and we'll just add it to the current note. Okay, so let's take a look at this. These graphs show me quite a lot of information. Okay, over here is torque, over here is angular acceleration, and it is fairly linear. And we expect that because Newton's second law says F equals ma, so it should make sense that torque is somehow proportional to angular acceleration. Now, the value of the slope in this case is 9.397 times 10 to the negative fifth. And if we think about that, that's 0.0000 0.9397. Okay, that's a fairly small number. It's almost 0.000 or 0.0001. Okay, if we come down to this one, we have 0.00024. Okay, and so we know that the mass of the first rotating disk was 106 grams, which is equal to 0.1 kilograms, and so this is not the mass of the rotating disk. However, this one was 212, so that's 0.212 kilograms. Okay, and so this slope to this slope is about double, which we'd expect because the mass was about double, but it's not directly proportional to mass. Okay, it's directly proportional to a different thing, and this different thing is called moment of inertia. Okay, and in fact, if we go back up to the lab, okay, you guys are going to have your analysis. Okay, there's some questions to answer about that. The thing that we just derived is almost Newton's second law, but it's called Newton's second law for angular acceleration. And Newton's second law says for angular acceleration is I alpha is net torque. Okay, I is moment of inertia. Okay, moment of inertia, and it depends on whatever is the rotating object. Okay, if it's a solid disk like we just did, it has a moment of inertia given by 1/2 mr squared. Okay, if it's not a solid mass, then it's going to have a different moment of inertia, and there's a chart of these in your book. But hopefully for now you're going to get your data plotted and you're going to come up with the moments of inertia of those two disks. I want you to do that. The slope of that line is the moment of inertia. So the last thing on this lab to do is find I for one disk and disk 2. Okay, I want those. I for disk 1 and I for disk 2. That's the moment of inertia. It should be the slopes of your line. Okay?